All right, this video covers Stat 454, Chapter 8.3, Maximum Flow Problems. So a thing we have been talking about generally is these network problems. In 8.2, we use the transportation simplex problem to solve these minimum shortest path methods. And now what we're going to talk about are maximum flow. So we can create networks that represent flow from one node into another node. So take a look at this network right here. There's a source node, a supply node, and from it is a amount of flow. You can see these flows being listed down here in this table. So for example, a flow of 2, a flow of 3, a flow of, let's see, from 1 to 2, of 3 right there, of 1 to 3 being 4, etc., etc. So there's flow out from the source, all flowing towards the sink. And in order to create a balanced problem, which is going to be necessary to solve these problems, we make a cool observation that all of the flow coming out from the source is going to be balanced mathematically by this A0. This is the flow from the sink back to the source, a hypothetical flow. And so you can start writing equations that represent these amounts of flow. So let's see right here. Notice these variables x, SO1, source to 1, being restricted by a flow of 2, SO2 being 3, etc., etc. Excuse me. These are all of the capacities right here. And then there are these balance constraints. So notice that each of these balances flow into a node and out of a node. You have one for every node. So let's go up to this figure. Let's take a look at node 1. Look at the flow into node 1. There's from source to 1, and it has to balance out from 1 to 3 and 1 to 2. So source to 1 balances out with 1 to 3 and 1 to 2. Source to 1 balances out with 1 to 2 and 1 to 3 right there. That is going to apply for every relationship of nodes. So for source, node 1, node 3, node 2, and the sink. And you can see them appearing right here. Source 1, 2, 3, and sink, as well as the usual xij bigger than or equal to 0. Now, we won't have a simplex method to solve these. So what we're going to need to do is use Octave or MATLAB to actually do the solving. So when you create, oh, hold on, before I go too much farther, I should say what the objective is. So the way we actually solve this is by making another clever observation that in order to balance out flow from source to sink with this node, with this arc from sink to source, that if we just track what happens at that final backwards artificial arc, then that's the accumulated effect of everything going in. So this maximize z equals x0 is the flow out from the sink, the hypothetical flow out from the sink. So what we need to do in order to actually use Octave to solve these problems is assign a name to each of these variables. And what you'll do is probably call these something like row column pairs. So I would call this variable x1, x2, x3, x4, x5, x6, and x7. And then I would go and rewrite all of these letters as the appropriate letter number pair that I did in the previous part. Once you do that, you can create your A equality, B equality, A and B in Octave. So let's try that here. Let me move this to the side. And let me click a new share. So this is Octave. And I've created a file named flow that will allow me to solve this equation. So remember that generally, you're writing something that looks like this. Linprog F A B A equality B equality lower bound and upper bound. So we need to copy this information over in a form that actually works. So I'll make a comment that makes all of these associated pairings. Maybe I won't do that because that would be a lot of typing for you to watch. How about I just create something like this? Let's see, 1, 2, 3, 4, 5, 6, 7. Like that. And I would repeat this process for all of the letters. And I obviously won't write every single one down because it would just be a video of 20 minutes of me typing impromptu. And you'll do a similar thing for these B's. Like that. Now, here's the tip I want to make for the A equality and the B equality. In the previous formula, or the previous page, take a look at the form of these equality constraints. It looks like they don't have a right-hand side. So what you should do is actually subtract values over to the opposite side. So instead of having x0 equals xso1 and xso2, you should subtract these quantities over. And you will have, line by line, things that look like this. You'll have a 1 here, and then a couple of negative ones, and then zeros for everything else. And because you did a subtraction over to the other side, you should have a 0 as the equality constraint, the right-hand side. And this will hold true for all of the B's, like that. And then on the equality for A, you'll have variations that look something like this, more or less. You'll have all of the subtractions over to the opposite sides, and you'll bring all of the coefficients over. You'll do this for every single row, every single constraint, until finally you fill out the equations. Remember, lower bound is going to be all zeros. And then upper bound on this one, because there is no upper bound of flow, you're going to have an expression that's empty. Okay. Obviously, these aren't the exact matrices. You're going to have to go through and create them one by one. Just label them appropriately and do all of the subtraction. So one last thing. Remember that this is a maximum flow problem, and linprog's default is a minimize operation. So on the minimize operations, you need to use the, on the maximize operations, you need to use the negative coefficient of f in order to actually perform the calculation. Let's see right there. Yep. linprog is a minimize function. Okay. Big ideas related here in these flow problems, the creation of this artificial flow arc from the source to the sink to balance out that problem, as well as rewriting the names of variables to help track all of the variables in the program. All right, that's everything I want to say about 8.5.